Good day. My name is Kaiser Fahade Ulama, together with my partner, Amanor M. Abu, and today we will tackle about Wellbore storage. So what is Wellbore storage? It is a function of the Wellbore fluid and the completion size. Consider the case of a drawdown test. When the well is first opened to flow after a shut-in period, the pressure in the wellbore drops. This drop in the wellbore pressure causes the following two types of wellbore storage. Number 1. Wellbore storage effect caused by fluid expansion. Number 2. Wellbore storage effect caused by changing fluid level in a casing tubing annulus. Part of the flow will be contributed by the wellbore instead of the reservoir. Q is equal to Q sub F plus Q sub WB, where Q equals surface flow rate, QF is equal to formation flow rate, and QWB is equal to flow rate contributed by the wellbore. Each of the two effects can be quantified in terms of the wellbore storage factor C, which is defined as C equals wellbore storage volume, and the other one is equal to change in the volume of fluid in the wellbore. The wellbore fluid expands as the bottom hole pressure drops. Therefore, the initial surface flow rate is mostly from the fluid stored in the wellbore rather than the formation. The wellbore storage as a result of fluid expansion is referred to as this. The formula for this type is C is equal to V sub WB CWB, where VWB is equal to total wellbore fluid volume and CWB is the average compressibility of fluid in the wellbore. The second type of wellbore storage occurs when the annulus fluid level changes, falling level during a drawdown test and rising fluid level during a pressure buildup test. The fluid level in the annulus drops when the well is allowed to flow during a drawdown test due to the drop in pressure. This annular fluid production joins the formation fluid production and adds to the well's overall flow. In most cases, a declining fluid level can contribute more fluid than expansion. Formula for this type: if A sub A is the cross-sectional area of the annulus, and P is the average fluid density in the wellbore, the wellbore storage coefficient is given by C is equal to 144 A sub A over 5,615 times P, with A sub A is equal pi to the quantity and the quantity of IDC squared minus OD sub T squared over 4 times 144, where A sub A is equal to annulus cross-sectional area, ODT is the outside diameter of the production tubing, ID sub C is the inside diameter of the casing, and P is the wellbore fluid density.
Wellbore storage effect caused by changing fluid level in the casing tubing annulus. So to determine the duration of the wellbore storage effect, it is convenient to express the wellbore storage factor in a dimensionless form. So we can see dimensionless wellbore storage factor is equals to 5.165 times wellbore storage factor all over 2 pi times thickness times porosity times wellbore radius squared times total compressibility coefficient is equals to 0.894 wellbore times wellbore storage factor all over thickness times porosity times wellbore radius squared times total compressibility coefficient. So the wellbore pressure is directly proportional to the time during the wellbore storage dominated period of the test and is expressed by the following. So where PD is equals to dimensionless pressure during well-bore storage domination time and TD is the dimensionless time. So taking the logarithm of both sides of the above relationship gives us log multiplied to PD is equals to log TD minus log CD. So time may be estimated from TD is greater than 60 plus 3.5 seconds CD, or TD is greater than the quantity of 2000 plus 1000 12,000 seconds multiplied to C all over H over U. So where T is equals to the time that marks the end of Weber storage effect and the beginning of the semi-log straight line in R. So K is the permeability in millidarcy, S is the skin factor, M is the viscosity or centipoise in centipoise. So C is the Weber storage coefficient, also BBL over PSI. Example: the following data are given for an oil well that is scheduled for a drawdown test. So volume of the fluid in well bore is equals to 180 BBLS. Tubing outside diameter 2 inches. Production casing inside diameter 7.675 inches. Average oil density in the well bore is 45 pounds per cubic feet. So H is equals to 20 feet. Well bore radius 0.25 feet. Permeability is 20 millidarcy. So CT or total compressibility coefficient is equals to 20 times 10 raised to negative 6 PSI raised to negative 1 or microsip. So porosity is 15%. So oil viscosity is 2 centipoise, skin factor 0, and CD or dimensionless well-bore storage factor is 10 times 10 raised to negative 6 PSI raised to negative 1 or microsip. So for the solution, so the first step is to calculate the cross-sectional area of the annulus A. So A is equals to pi multiplied to the quantity of 7.675 squared minus 2 squared all over 4 times 144. So we can get 0.2995 square feet. So in calculating the well-bore storage factor caused by fluid expansion, we use C is equals to well-bore volume of fluid times well-bore coefficient, storage coefficient. So C is equals to 180 times 10 times 10 raised to negative 6. So we get 0.0018 BBL PSI. So to determine the well-bore storage factor caused by the falling fluid level, so C is equals to 144 times cross-sectional area of the annulus A all over 5.615 B, or the average oil density in the wellbore. So C is equals to 144 times 0.2995 all over 5.615 times 45. So we can get 0.1707 BBL PSI. So for the final solution, calculate the total wellbore storage coefficient. So all we need is just to add. So C is equals to 0.0018 plus 0.1707. We get 0.1725 BBL PSI. The calculation shows that the effect of fluid expansion can generally be neglected in crude oil systems. So determine the time required for wellbore storage influence to end from. So T or time is equals to the quantity of 200,000 plus 12,000 seconds multiplied to C multiplied to viscosity all over permeability times thickness. So D is equals to 2000 plus 0 multiplied to 0.1725 times 2 all over 30 times 20. So we get 115 Rs. That's all. Thank you.